In the earlier video, we have seen statistical learning, at least in the supervised learning approach. And we have seen linear models for regression and generalized linear models for classification. In this video, we are going to expand now to a type of predictors which are differentiable end-to-end. So we are not going to be requiring just a loss function to be differentiable with respect to the parameters, but we're also going to be requiring all of the components of this prediction architecture to be differentiable with respect to parameters. These predictors are part of what we call the connectionism philosophy, where we are actually putting together individual units that we'll call sigmoidal neurons, that when they are connected together in a proper way, that we'll see exactly what proper means, they are exhibiting some, I will call it, universal approximation properties. So let's get started with introducing just a single sigmoidal kind of neuron. And let's go to the site. So the actual neuron that we see here on the site, on the top figure over here, is a fairly complicated kind of organism. It has inputs that we call dendrites and outputs. And in between inputs and outputs is actually this compressive stage that is called myelinated axon. And signals are actually going from those dendrites through this axon into outputs. And this neuron, this unit, is going to be connected to other units that we'll see in a moment. Now, Rosenblatt, working in a government-sponsored laboratory 60 years ago, he actually came up with an architecture that kind of resembles this organism. And we have seen this type of architecture before. So let me just write the kind of a diagram on our sort of board right now. This first kind of stage of this neuron is a dot product, the sigmoidal neuron that is. There are various kind of neurons, but here we're just treating the sigmoidal version. So we have the dot product of W transpose X. These are both vectors. And explicitly, we are sort of denoting here this kind of a bias term that is kind of explicitly shown as B. And the last stage is a nonlinearity, which is the sigmoidal nonlinearity that we have also seen in the treatment of logistic regression. So typically, this signal over here is called activation. And this is also known as activation function. And evidently, just like in everything we have done up to now, we have a y hat at the output. That is the predicted target variable. And also, we know now that corresponds to the probability of y is equal to 1 given x. Okay, so that is basically the block diagram of the sigmoidal kind of neuron. And I hope everyone is kind of familiar with the dot products and all this kind of discussion we had even from kind of earlier kind of treatment. So I'm not going to expand here. What I think is worthwhile actually doing, however, is to try to understand how potentially a neuron with everything we have seen can be trained. And for that, I'm going to go into web page actually called TensorFlow Playground. And in that TensorFlow Playground, we're going to see now how we can actually take this kind of neuron, this block diagram, and hit it with some kind of a data set and see what it is able to do and how it will probably not able to do certain things for us, and have some discussion about how we can actually create a network of these neurons. So when you actually go to the site, TensorFlow Playground site, we'll actually, the first time you go into there, you'll actually see a picture such as this. And we'd like to modify this picture to just basically bring a single neuron into that. So we will have here just press the minus button to eliminate what is called a layer, which a term that we'll see shortly, and just leave a single neuron on that sort of architecture. We have a single neuron architecture. We are going to have a sigmoidal activation function. And we are going to be discussing the operation of this kind of neuron in this small data set that we see here. It's a classification data set with just 2 classes. And just because we would like to make things a bit more challenging, if you can increase the noise to something like 25, you actually get a non-linear separated data set. And that is basically it. We're going to have a potentially a batch size of 10. Okay, let's leave it 10, or even we can make it 1. And we are going to avoid introducing complications of regularization here. Learning rate, as we have seen earlier, should be some small number, let's say 0.01. And we just by pressing the play button, what you actually see, you'll actually see the output over here. This is the loss function, the two loss functions, the training loss and the test loss, that are very, very quickly converging. And this is the decision boundary that the single neuron kind of produced. Very straightforward, very easy to come up with, if you like, that decision boundary, as you can see. And of course, everything that we have discussed before, the stochastic gradient descent, is in operation here. So if we go back to that drawing board, you will definitely expect to see here a loss function, which is nothing else as the binary cross entropy. And that binary cross entropy being fed into the stochastic gradient descent, that it will adjust the weights W from one iteration to the next. And that is all straightforward. We have done that before as well. And now let's go back to that site and let's see what is going to happen if we change a little bit the data set we are facing. And we have another two-dimensional data set. I forgot earlier to mention that here we have effectively 2 features, 2 dimensions in my X. We have X1 and X2. Again, in this new data set we have, which is slightly more complicated, let's first of all remove the noise just to see, the data set a bit more clearly. So we have the blue class kind of centered in the middle, and it is surrounded by the orange class. And as we expect to see, the decision boundary is definitely heavily nonlinear. It's actually, in fact, circular. And let's try to do exactly the same thing. Press the play button and see exactly what is happening. So we observe now a kind of different behavior. We are going to start seeing some form of loss reduction. So the neuron is actually trying its best to minimize training and test losses. And here we kind of see some kind of a decision boundary, but I hope we all recognize that that's not really the one that we are probably going to result into a very good prediction performance and a very good generalization. So what is to blame here? And we have seen this kind of behavior before, even in the linear models we have studied, and this is effectively what we see here is some form of an underfitting effect. In other words, the single neuron, in terms of the number of parameters, we have 3 parameters here, 2 associated with the number of dimensions of X plus the bias term, is really not able to capture the complexity which is required by the target function. And that underlying target function that governs this kind of classification problem requires probably a larger number of parameters. So that's a kind of a good pretext to start introducing neural networks. Now we are going to start interconnecting many neurons together in some architecture that will make sense to all of us. All right, so let's see. We will now use the single neuron that we have seen as a unit. So I'm drawing, if you like, a single box over here. I'm putting the number 1. And inside that single box is everything that you see here above. all of these blocks are inside this kind of single block. We are going to feed to it the x that we've seen in this TensorFlow Playground example, and we are going to feed x also to yet another neuron. Let me just draw it a bit kind of differently to have a bit more space. And this is the second neuron. The first neuron has parameters that are inside it are W1 and the associated kind of bias. Now, to make the math a bit easier, I'm not going to be dealing with the bias term explicitly, at least in this discussion. So I'm just going to show you only the weight W, the parameter W vector, which is 2. The dimensionality of that is 2, just like the dimensionality of x is 2. So the first neuron will produce an output of, I will call it y1. And the second neuron will produce an output which we'll call y2 hat. These are the two predictions. However, now these outputs will be combined with the help of a third neuron, neuron number 3, to produce the final output which we'll call y3 hat. And this neuron has its own kind of parameters, w3. Okay, so that's basically the architecture we are going to study a little bit. And okay, so that, I think, architecture, this actually makes sense. We are going to definitely have a scalar at the end. This is a scalar, this is a scalar, two scalars in the form of a vector. So at the input over here, we see a vector. This vector, we'll call it, let's call this vector h. This vector h is consists of y1 hat and y2 hat. This vector will be dot product, we form a dot product of h with the w3 over here and follow with the sigmoidal unit. So the output of this architecture is going to be, this 3 neural architecture is going to be a scalar, which of course is exactly what we need for binary classification, a scalar between 0 and 1. All right, so in terms of terminology, we'll be calling this stacking of neurons, let me draw it like this, we'll be calling this a layer. So effectively here we have 2 layers, and more specifically, this layer, which is just before the final stage, we are going to also be calling it body sometimes, because this body will consist of more than 1 layers typically. Here we just have only 1. And this part over here will be calling it a head. And more specifically, this head is a sigmoidal neuron which is doing classification. I will call it classification head at this moment. Okay, so if we are to write down the equation of the y3, this is sigma of w3 transpose h. That's the equation of the neuron number 3. That is exactly the functional form of what the neuron 3 is actually doing. So here we have sigma, and open parenthesis, we have w1 w2 the second component of w3, transpose times the h1 and h2, the 2 components of the h vector, which is nothing else than, let me write it the way I wrote it over here, y1 hat and y2 hat. And this is now sigma of w1 3 y1 hat plus w2 y2 hat. And this is nothing else now as sigma w1 well, the y1 hat itself is another sigmoid function acting on the dot product of the first neuron. Okay, that's basically my x. And this parenthesis should not be there. Plus w2 sigmoid of w2 transpose x. That is actually the expression of the output of this kind of network, of this 3-neuron network. And there are some kind of interesting observations just from this kind of simple architecture that I would like to point out. The first is that we definitely see some form of nesting going on. So we have some kind of a nested function. We have sigmoids of sigmoids. We have sigmoids of some linear combination of other sigmoids, which are evidently nonlinear functions. And if you recall from all our earlier kind of work on generalized linear models, we always had this kind of form of W transpose phi of x. Now, this phi of x is at that time came from the sort of well-established basis functions such as polynomials and so on. Over here, what we see is that these effectively are the features taking the place of these phi functions we have seen earlier. So we have two features over here combined linearly. So feature 1 and feature 2. And perhaps more importantly, this head, this is accepting and combining features, and these features have been generated from within the network itself. So the network is effectively constructing the right features such that the classification head at the very end is able to actually do this job properly. So that's actually a kind of a fairly important observation of what we seen earlier and the comparison what we have seen earlier and what we actually have right now. The second point, so the first one is nesting. The second one is sort of, I will call it automatic feature generation. And the third one, which I wanted to mention, is that now we have going to have exactly the same environment which we have seen earlier in our parameters, parameter optimization. So we have evidently a binary cross entropy and a stochastic gradient descent, but now everything is jointly optimized. So I am going to be writing here the theta vector, which consists of three other vectors, W1, W2, and W3 of these three neurons. And the optimizer is going to be jointly optimizing the parameters, just like we have seen earlier from just a single neuron. And therefore, it will be implementing the well-known to us equation of stochastic gradient descent that we have seen earlier. So I'm mentioning that because very quickly, the number of parameters that we have here will explode. So here we have how many? We have just basically 6 parameters here, plus the 3 bias terms, which I didn't write explicitly, let's say 9. So this stochastic gradient descent will actually be searching in this 9-dimensional kind of space to find this optimal theta star gradually, as we have discussed before. So the important thing is I think number 2, the automatic feature generation, or the fact that the network itself builds the right representations for the head, or whatever the head is doing. The head in this case is doing classification, but we'll see other examples where the head is actually doing regression for the right task. The task is the responsibility of the head to implement it, and definitely we see here a good small example, but it actually taught us a couple of things we have not seen before. To close the discussion, we'll go back to that site, TensorFlow Playground, and recreate the architecture we had put together. So we were going to have two layers, and in the first layer is going to consist of two neurons. Both neurons accept exactly the same X as it's actually shown over here, and the output of this each neuron is being combined by the head. That's the last neuron at the top of the layer, if you like. Okay, and now we are going to sort of play again with this experiment, in this kind of more complicated experiment data set that we have seen earlier, that a single neuron was not really able to do much. And we are going to just press the play button and see what happens. So again, the stochastic gradient descent is now looking at this kind of a 9-dimensional space, and continues to look. We are evidently going through many epochs. Our training loss and test loss seem to have been stuck at around 0.5. So not really a very good sort of behavior yet. But we should also be patient, because, you know, this thing is actually running in the browser. It is using, the kind of V8 engine, which is behind this browser to do the calculations in kind of a JavaScript. So it's not really the fastest implementation. And since we are looking in this 9-dimensional space now, I think we should give it some time. Yes, surely enough, some local minima seems to have been found at this moment. So the loss kind of dropped. We start seeing some elements of loss function being significantly now dropped. And look what happens now with the decision boundary. The decision boundary, without really us doing that much, and then really adding these neurons, became kind of quadratic. And it's kind of almost there in a sense that it is, all we need to understand is whether if we can give it some more time, perhaps another local minima, which is even better than the one that we have just experienced, will be found. And we are going to just let it run. And however, we can actually show some kind of a useful trajectory now in front of us. We have seen, as we are adding more neurons, then effectively we are enhancing the modeling capabilities of our hypothesis set. So we should have now some analogy in our mind. What we have seen in the earlier as a hypothesis set, and the set of functions G that we have discussed is actually translated into an architecture. So the more complicated the architecture becomes, perhaps the more we increase the number of hidden layers, or even the number of neurons which are in each layer, then we would expect to see an ability to sort of fit more challenging target functions. So let's play this with for a while. Let's leave it running over there, and then if it finds a good local minima, and we can actually stop the iterations and present it to you. All right, now from actually let it run, and then from that kind of perspective, I think the next discussion would actually be to try to create a mathematical abstraction of this networks that will be calling fully connected networks. So we need to understand why we call them fully connected.